Good morning, afternoon, evening, whatever the heck it is. It's Dr. Carroll here. It's Chem 1111. We're looking at Lecture 4 today, Chapter 8, Phase Changes. It's just a phase we're all going through, isn't it? In your textbook, this is on page 395, and let's start with the slides today just to get a bit of a overview of what we're going to look at. We're going to look at enthalpies of phase changes in terms of intermolecular forces. Now remember, phase changes can be solid to a liquid, solid to a gas, gas to a liquid, gas to a solid. And you could also have phase changes between different arrangements of solids, which is interesting. And we can interpret a pressure temperature phase diagram of a pure substance. So we're going to look at phase diagrams here. And recall there's three states of matter: solid, liquid, gas. Yeah, there's plasma. We don't care about that in this course. Transformation from one state to another is called a phase change. If you're pouring energy in, it's endothermic. If energy is released, it's exothermic. And here we have just a liquid. Let's say it's water at 25 degrees Celsius. We ramp up the temperature. We could use the heat capacity equation. Specific heat times the mass times the temperature difference, and then we're going to break the intermolecular forces. That's our plateau region. All the energy is being used to break those forces, so the temperature stays constant till all the liquid has been vaporized, so that you get your delta H vap over there, and then you could make the gas even hotter as you go ramping up the temperature some more. We have the molar heat of vaporization, which is how much energy is needed to vaporize 1 mole of a substance at its normal boiling point, which is 1 atmosphere. Actually not 1 bar, but still 1 atmosphere. So that's a relic of the old system. Molar heat of fusion. Fusion means melting. The heat needed to melt 1 mole of a substance at its normal melting point. And the molar heat of sublimation, SUB, is in substitute. It's sublimation. The heat needed to sublime 1 mole of a substance to make it to go from a solid to a gas. In the old days, we also said gas to a solid was sublimation. Now we call that deposition. And we just use sublimation for being a solid to a gas. And conservation of energy says us that sublimation, delta H of sublimation, is vaporization plus fusion. Is that right? I guess so. Solid to liquid, liquid to a gas would be solid to a gas. Yeah. Okay, we'll get to an example in a minute. Let's look at what our mini text says. It depends on intermolecular forces. Okay, we just had that picture, so I'm going to go through here. Note that the amount of heat required to vaporize a substance depends on the size of the sample. So that's an extensive property. If we just say, how much heat is needed, twice as much energy is required to vaporize 2 moles of water than 1 mole. But if you want to get intensive, then you have to have per mole. So the heat needed to vaporize 1 mole of a substance at its normal boiling point is called the molar enthalpy of vaporization. The nickname is just the heat of vaporization. Okay, so you got to pour in energy to overcome the intermolecular forces that hold the molecule together. If we're talking about iodine, then they would be dispersion forces, right? Be a molecular solid. If we're talking about delta H fusion, fusion and vaporization are the most familiar, but sublimation is also common. Solid going directly into a vapor without passing through the liquid phase. So dry ice sublimes at 195 Kelvin with delta H sublimation at 25.2 kilojoules per mole. I just watched some cooking show called Nailed It on Netflix, where they used dry ice in a beaker. It wasn't a beaker, it was a flask, but they called it a beaker. They wanted people to be scientists. That was their motif for that show. I have no idea what year it is and if that show's on anymore, if there's still Netflix, but back in the day, that's what was going on. Mothballs contain naphthalene, a crystalline white solid that sublimes to produce a gas that repels moths. Okay, so some interesting stuff. Then we have here at table 8.5, we have some temperatures and molar enthalpies of phase changes. And we see all sorts of data that can be helpful. And we'll use that. Phase changes can go in either direction. Steam condenses, so that's exothermic, and liquid water freezes. Steam condenses upon cooling. Liquid water freezes at low temperature. Each of these is exothermic because each is the reverse of an endothermic phase change. Heat is released as a gas condenses to a liquid and as a liquid freezes to a solid. To make ice cubes, for instance, water is placed in a freezer that absorbs the heat released during the formation of ice. So the values are just the negative of the opposite. So delta H solidification is the opposite of delta H fusion. Delta H condensation is the opposite of delta H vaporization. Okay, so what's happening here? A swimmer emerging from a pool is covered with a film containing about 75 grams of water. How much heat must be supplied to evaporate this 75 grams? Okay, so we have a table 8.5 which tells me that the heat of vaporization of water is 40.79 kilojoules per mole. So I got to convert that 75 grams into moles divided by 18.02. That's my molar mass of water. So I got 4.16 moles times 40.79 kilojoules per mole. So you have to supply N times delta H vap. There it is. There's my equation. QP, constant pressure, is N times delta H vap. 170 kilojoules is what is needed to evaporate the water, and then everything's good. If the swimmer's body must supply all this heat, a substantial chilling effect occurs. That swimmers usually towel off to reduce the amount of water that must be evaporated or lie in the sun, to let the sun provide more of the heat required. And you can deal with the ice cube on your own. No, actually, let's try it. Fine. So we want to try to determine how much heat is involved in freezing 125 grams of water in an ice cube tray. So QP is N delta H. Now this one is going to be fusion, right? That's, I mean, what's the opposite of fusion? So I can take care of the signs after. So fine, you want to put negative? Go ahead. So it's 125 over 18.02. Then delta H of fusion isn't going to be as much as delta H vaporization, because delta H of fusion is going from a solid to a liquid, which isn't as much energy as going from a liquid to a gas. And so now I got to look it up in table 8.5, and I find it to be 6.01 kilojoules per mole. So 125 divided by 18.02 times 6.01 is 41.7 kilojoules from the tray to the freezer compartment. So that negative sign means it's going from the tray to the compartment in the freezer. Okay. If you want to know more about freezers, you can go to my podcast series called All This Science. I think a few of you have contributed, done some excellent work on that podcast, and there's something about freezers on there, which is pretty cool stuff. Okay. Okay, I've said all this before. If we're talking about water baths here, but you can get different. If you want to have things happen at colder temperatures, you can use dry ice, which is minus 78. Liquid nitrogen, where you can have a bath at minus 196 degrees Celsius. Liquid helium, well, that's ultra cold stuff. Okay, so our last topic in this chapter is on phase diagrams. This is something I doubt you've seen before. It's interesting. This is also called PT graphs, because you put, and they're usually not to scale, you put pressure on the y-axis and temperature on the x-axis. Phase diagram shows which phases are the most stable at any conditions of temperatures and pressures. Chemical engineers use these fancy kinds for different situations, and so it's used by all sorts of people. Pressure on the y, temperature on the x. In the upper hand region, you have low temperature, high pressure. The substance is stable as a solid. So low temperature, high pressure. Okay, so what we're drawing here is a phase diagram. In the lower right hand region, we got high temperature and low pressure. And that is going to be a gas. In the intermediate states, we have liquids. So what the heck is going on here? We have boundary lines between the phase, separate the regions where each phase is stable. So here's a boundary line here down to here. So that means along there we have a solid liquid equilibrium along this fairly steep line over here. This curved line here, we have sublimation from, here's 0, 0. Sublimation, as we increase the temperature, temperature increases as we go this way, pressure increases as we go up. So anyways, along this line you have a equilibrium between the solid and the gas, and going the other way, deposition from the gas to the solid. Okay, then we have another curved line here, which is a boundary line between liquids and gases. So between liquids and gases, we have a region which is in equilibrium. So you have vaporization to the left, condensation to the right, melting to the left, freezing to the left, and the fusion line. So you just go across the horizontal. You are, if you're in the gas, you're expanding. And then we can also ramp up the pressure at a given temperature. So there's lots of things we can do. 1.01 bar is about 1 atmosphere. And if I go across there, that's my normal melting point. So there I can get the normal melting point and read that off going down here, right? So that's my normal melting point corresponding to 1 atmosphere. It's a melting point because it's between solid and liquid. If I keep going across, keeping pressure constant, then I can look at the this difference between the liquid and the gas phase, and that's the normal boiling point, and I can read off that value. So those are some interesting values. Here's a super interesting value here, a triple point. At the triple point, which is sometimes very hard to get, you would have the solid, the liquid, and the gas all present at the same time. And I'll show you a YouTube clip involving butanol, tertiary butanol, where you have the solid, liquid, and gas together at the same time. Or you can look that up on your own if you want, of course. What else is there? If I go at a real high temperature, I can get what's called a critical point. And past the critical point, you get a supercritical fluid, which means you can't get back from the gas to the liquid if you're at that temperature and pressure. You got to decrease the pressure and then decrease the temperature. Or you have to make things happen. You can't just get from the gas to the liquid if you're in this supercritical region. And this is actually used in some decaffeination processes. So for getting decaffeinated coffee, you can use supercritical fluid. Most slopes in the liquid, solid liquid line slope positive like this, but there's a few, especially water, which is negative, and that has to do with the hydrogen bonding and the density. So That's a clue for water. So most of the questions, they just ask you to follow what happens. Like if I'm at this pressure, what happens as I increase the temperature? Well, it's a solid. Oh, now I get a solid liquid equilibrium. Oh, now it's a liquid. Oh, now it's a liquid gas equilibrium. Oh, now it's a gas. Or at this temperature, whatever it is, what happens if I keep increasing the pressure? Oh, it's a gas. Oh, now it's a gas liquid. Oh, now it's just a liquid, and that's the end. Or here, oh, it's a gas. Oh, now it's a solid, and that's that. Okay, so those are some of the kinds of questions that you find. Now these points here, I've said all of them. I'm not going to repeat all this. 1.013 bar, is that what we had there? Oops. 1.01, yeah, okay. Boundary lines, triple point, yeah. Although two phases are stable under any of the conditions specified by the boundary lines, three phases are only stable at one point. Okay. Critical point, the distinction between gas and liquid disappears. Substance is supercritical fluid with viscosity typical of a gas, density typical of a liquid, and ability to expand or contract like a gas. So that's interesting stuff. At the critical point, as the temperature changes at constant pressure, you draw a horizontal line. If you want the pressure change at constant temperature, you draw a vertical line. Temperature for conversion between vapor and condensed phase depends strongly on pressure. Okay. Qualitatively, this is because compressing a gas increases the collision rate and makes condensation more favorable. Okay. Well, the melting temperature is almost independent of pressure. Okay. Pressure has hardly any effect on liquids and solids. Solid vapor boundary line extrapolates to zero pressure and zero temperature. At 0 Kelvin, the molecules have minimum energy, so they can't escape from the solid. At 0 Kelvin, the vapor pressure of every substance would actually be zero. Okay, so here we have figure 836, a drawing for water, and we see that here's my melting point, 273.15 Kelvin, and if I go to a if I lower the pressure, the melting point is going to go up a little bit. It's not a big deal, but it goes up a little bit. And here's the boiling point, and you see here that if I lower the pressure, then it'll boil, the water will boil at less than 373 Kelvin. And we have a triple point here, T triple. It happens at 0.0061 bar, which is hard to get. Okay. Sufficiently low pressure, ice sublimes but does not melt. The dashed lines show two paths that involve phase changes for water. The horizontal dashed line shows what happens as temperature increases. As ice warms, it remains solid until it reaches 273.15. The solid ice then melts to liquid water, and water remains liquid as the temperature increases until it goes to 373.15. Then it changes to water vapor. The pressure is 1.1 bar. Water is most stable in the gas phase at all higher temperatures. The vertical dashed line shows what happens as the pressure on water is reduced at constant temperature. Water remains in the liquid phase until the pressure drops to 0.03 bar, and then it's more stable in the gas phase. No, nothing stable in the solid state there. All the phase diagrams share the 10 common features, but the appearances can be different because of the strengths of the intermolecular interactions. We have here example on the left. What is this guy? nitrogen, N2, there it is, molecular nitrogen, and carbon dioxide on the right. So you see the curves are different, and that's okay. There's different intermolecular forces. Triple points for N2 and CO2 are well below room temperature. And so then you can go through, slide them all around. Here in example 8.9, you can construct a phase diagram. Ammonia is a gas at room temperature and pressure. So its normal boiling point is 239.8 Kelvin, and it freezes at 195.5. So you can start making marks here, right? Normal, so 1.01 bar, melting point 195, boiling point 239, triple point 0.061 bar, and then you start connecting things up. And sometimes the scale has to go out of whack. Sometimes you break a scale, but otherwise you couldn't get everything on the graph. So you can get some practice on that. Here in example 8.10, we have a synthesis in which a vessel at 0.5 bar, so that's over here, using liquid ammonia has a solvent. What temperature range would be suitable? So I guess between 195 and 235, right? Because then it's a liquid. Because the chemist wants to work at 0.5 bar, draw a horizontal line across the phase at 0.5 bar. The top figure is an expanded view of the phase diagram between 150 and 300. It intersects. So here's my solid liquid, here's my liquid gas. The horizontal line intersects the boundary lines at about 235 and 195 Kelvin. So liquid ammonia is stable there. At the completion of the synthesis, the chemist wants to remove the solvent without removing the temperature past 220. So to remove the solvent, you want to go to gas, you want to start decreasing the pressure, right? A vacuum pump capable of reducing pressure below 0.25 bar. Okay, so you want to get it below 0.25. Why is that? Chemist wants to boil off the solvent without raising temperature above 220. So here's around 220. Yeah, 220 is around 0.25. So use a vacuum pump to decrease the pressure, and then the solvent will evaporate or vaporize. Okay. Then you can try the next one on your own. Geologists use some fancier phase diagrams. We won't worry about these, but look at these ones here. You got different phases, so different arrangements of the salts. You've got alpha quartz, beta quartz, coesite, stishovite. Be careful how you say that. So you get some more interesting stuff there. And you can try the section exercises on your own. Okay? So that's the end of Chapter 8. We looked at the effects of intermolecular forces, types of intermolecular forces. What else did we look at? Liquids, forces in solids, order in solids, phase changes, and phase diagrams. Okay, let's see if the slides tell us anything useful. Triple point, critical point, general phase diagram, example 8.9. Okay, we looked at that one. Variations on phase diagram, visual summary. And there we have it. Okay, so try some of those questions. Have a good time.